In this video, I want to talk about, I want to give an introduction to something, to what Mueller calls Bizarro Hodge structures. So Mueller's Bizarro Hodge structures. So first, let's recall. I want to give you the basic version of this, and so this is all things that I've been told, that have Alex has told me about. So if I get anything wrong, it's my fault. So theorem. Okay, so let's just recall this. I have some videos on this. So there's this Ax-Katz Chevalley-Warning. Okay, and so what this says is that if we have X is a smooth projective variety over FQ, and they'll say Q is P to the R and P is a prime. What it says is that the number of FQ points of this variety, or FQ to the, now I need a new letter, S points, is going to be congruent to 1 modulo a certain number, Q to the nu here. And so this number here, nu, is going to be the Hodge level. And so this is the first non-vanishing. So I think this is correct. So this is the first non-vanishing of so the index of first non-vanishing of cohomology in the Hodge diamond. So the index, and so you kind of take all the HIJs, and then you take the minimum I, where there's one of them that's not 0. Okay, so this is what we have here. So there's this theorem, and this theorem is actually implied by another theorem that's about. So this is, by the way, this is implied by Mazur's theorem. So this is the Newton above Hodge theorem. This one, so there's a Newton polygon and a Hodge polygon. So this has to do with, so the multiplicity, so order P eigenvalues, so number of order P is equal to I eigenvalues of the Frobenius. So it kind of counts the multiplicity. I mean, by multiplicity, I mean the p-adic order, or the p-adic valuation of the eigenvalues. And then this thing here has to do with these Hodge numbers, Hij. So you do this at a fixed W. So you fix a W, and so you do this for a single cohomology group, and then you compare them, and it says that this polygon is going to be above this polygon, and when this one is up, it means that there's going to be lots of eigenvalues whose p-adic valuation is going to be a given number. Okay, and so there's this theorem, and this Mazur's theorem implies this Ax-Katz Chevalley-Warning. There was a proof before this theorem was proved, and actually this thing was conjectured by Katz because of some of the techniques that he used in proving it. Okay, so that's a quick review. So the bizarro part is that so let me tell you the weird stuff now. The weird stuff is what what Alex did, and so this kind of builds on work of Katz, and so this is Katz, and it says that if you take a curve and this is this, and so this has so we take the projective model, the projective model, and with one, so it has just one ramified point at infinity, one point at infinity. What it says is that we'll view this. Okay, so we view it over FQ. Q is going to be p to the r again. R is going to be a prime number, and it says that when we look at the f q to the s points here, so that's going to satisfy a congruence. It's going to be congruent to 1. Well, it's going to be 1 modulo mod q to the this number here. So it's going to be q to the n minus d over d here when d doesn't divide n, and it's going to be mod q to the nu when d does not, when d does divide n. Here nu is going to be equal to 1 over d, and so the point here, okay, so this is the theorem. This is the theorem. And the magic thing about this theorem is that this number here, this is like a non-integral Hodge level. So it's behaving as if well, it has a fractional Hodge level. Oh, and so one of the things that I want to kind of say is how this works, the idea of how this works, and some of the things behind this. And so the philosophy here is going to be that the cohomology of this so like the étale or crystalline cohomology of this ring have more symmetries than it should. Okay, so that's the kind of the introduction to this. I'm going to stop the video here, and then I'm going to continue with explaining some of these things. Thanks for watching.